Good afternoon and welcome to the CERIAS Security Seminar. Our speaker this afternoon will be David Zage, who's a PhD candidate in the Department of Computer Science. David, take it away.
Thank you. So today I'll be presenting some of my thesis work entitled A Platform Creating Efficient, Robust, and Resilient Peer-to-Peer Systems. Just as a note, feel free to raise your hand and interrupt if you have questions. I'd rather answer them as you get them than save them to the end. So just let me know if you do have questions. So first we'll look at a bit of background. And so recently there's been a large growth in communication networks such as the internet. And along with this growth, there's been a large growth in number of users as well as devices. By the year 2015, there are supposed to be over 15 billion network devices and somewhere close to 4 to 5 billion network users. So along with this explosion in the number of devices and the interest in networking in general, there's been a large growth in the number of peer-to-peer applications. There's file distribution such as BitTorrent, voice over IP such as Skype, internet streaming such as ESM and PP Live, as well as distributed computation such as folding at home. And if we actually look at the graph on the right-hand side of the image, we can see that in the year 1998 there was almost no peer-to-peer traffic. However, by the year time 2004 rolls around, which is the newest data that we have, that nearly 50% of the traffic going across the internet consisted of peer-to-peer traffic. So in order to enable these applications, many peer-to-peer applications are built on top of overlay networks. And overlay networks have been proposed to increase and improve the performance of these applications, as oftentimes the end-to-end paradigm that the internet has is not sufficient for providing the service guarantees that the applications need. In essence, an overlay network is just a collection of nodes connected by a set of virtual links, and these virtual links may consist of one or more actual hardware links. And what overlay networks provide is they provide increased capacity. As more nodes join the network, they have greater computational power and greater storage. As more nodes join the network, there's increased performance because of the increase in computational power and things like RAM. And finally, there's increased reliability. There's more storage, so obviously you can store information at multiple points in the network, as well as multiple virtual links can connect nodes, adding to the redundancy in the network and redundancy in routing. So with this large growth in peer-to-peer networks and overlay networks, there's been a focus on actually getting these out in the public and actually getting these to be high performance and well liked by users. This includes working on things such as adaptivity mechanisms and network awareness and incorporating these into the peer-to-peer systems. However, there's been little work on actually creating robust and resilient systems in adversarial environments. Oftentimes, these systems are designed to be deployed in benign environments where all the nodes cooperate, and that oftentimes the proposed systems and mechanisms are vulnerable to attack. So these attacks actually come from two main points. The first is that peer-to-peer applications are deployed in open environments. As I was saying, these applications are often deployed across the internet, which makes them vulnerable to malicious attacks coming from outside the network. And secondly, peer-to-peer applications push the trust of the network towards the fringes of the internet, push it towards the end user nodes, which have been shown to be more insecure. So this means that the systems themselves are actually vulnerable to malicious attacks from inside of the application. So they are actually vulnerable to attacks from users that have legitimate access to the system. What this means is the fact that traditional security mechanisms such as digital signatures and access control are not actually enough to provide security for the system. So this talk will focus on enabling secure, resilient, and high-performance peer-to-peer systems in adversarial environments through the creation of robust system components. We want to look at reconciling the performance of the security of peer-to-peer systems with and identifying and characterizing three critical components. The first being network awareness, the second being intelligent adaptation, and the third being responsiveness to identified threats. And today we'll actually look at the first two. So the first component is looking at robust network awareness. And robust network awareness, in essence, is the ability of an application to measure the network around it and take the measurements into account and make decisions on how to provide better performance for the user or for the system. often, many of these systems today actually are able to provide network awareness, but in heavyweight manners. A system will have each node probe a subset of the entire network in order to gain information about the network, and then use this information to make better decisions or to adapt the structure of the system. However, this creates a lot of overhead in the system, and it's not actually going towards the end goal, providing a service towards the user. And if we have multiple systems running on the network, then this overhead is actually incurred for each of the systems. So in order to provide a lightweight mechanism for providing network awareness, virtual coordinate systems have been proposed. And these allow hosts on the internet to predict the latency between an arbitrary host in a scalable manner. Basically, each host in the network is provided with a coordinate, and the difference between these coordinates is at the estimated round-trip time between two nodes. If we look at the bottom of the screen, we can see an actual topology of just 4 simple computers, and each connected by links around the outside as a link to the middle. Now, actual measurements have been conducted across the outside but not through the middle, and the gray servers wish to communicate. They're trying to determine which link will provide them the best performance. If we have a coordinate system, they can simply take the difference between their two coordinates and find out that the middle link is the shortest link without having to do any additional probing of the network. The accuracy of these systems is measured by the prediction error, and 2 main architectures for the systems have emerged. One being a landmark base, which has fixed points from which distances are calculated, and the second is a completely decentralized version. As peer-to-peer systems are decentralized and oftentimes do not have any centralized structure, we focus on these type of systems. So as I was saying, they have no fixed infrastructure nodes, and while there are many different types of decentralized virtual coordinate systems, they have 3 common characteristics. The first being a reference set or neighbor set of nodes. This being each node in the network is assigned a reference set of nodes from which to receive information from. So it'll periodically probe these nodes in order to gain information like the round trip time to the node as well as that node's coordinates. A distance prediction mechanism. The coordinate system is actually takes real latency estimates and embeds them in a Euclidean or non-Euclidean space, and so the distance prediction mechanism is simply the Euclidean distance between 2 points. And finally, an error minimization technique. In order to minimize the error occurring in the entire network, these systems use an error minimization technique. Oftentimes, newer systems use things based on physical constants, such as, for example, if we imagine that every node is connected to other nodes by springs, we want to relax the tension on the springs across the entire network in order to minimize the error in the entire system. Some example systems include Vivaldi, pick, and p-chord. I'll go over Vivaldi in a few more in the slides, coming slides for a little bit more detail and a little bit more understanding. And you should note once again that the accuracy relies on the assumption that these nodes behave correctly with the protocol. So here's an example, or here's a more in-depth description of the Vivaldi virtual coordinate system. So as I was saying, is it takes latency measurements and actually embeds these measurements in a multi-dimensional Euclidean space. Here we use 2D examples just for ease of use. We can use multiple more dimensions if we wish for better accuracy. Each pair of nodes is logically connected by a spring, and the length of the spring is simply the estimate of the round-trip time between the two nodes, and the tension on the spring is the error. If we look at the top graph, we can see that the anchor node is connected to the green node, and it has an estimated round-trip time of 50 milliseconds as shown by the spring, whereas the real round-trip time is 20 milliseconds as denoted by the blue arrow. Now, in order to actually make this better and actually make the estimate more accurate, what will happen is the green node will actually move towards the node that it probed, being the anchor node, and so it updated its position based on the received information. So here we can see that now in the bottom half of the picture, we can see that the estimated round-trip time is 30 milliseconds, whereas the actual is 20. And we can see this is a much closer estimate. The reason that it didn't actually have the estimate match the actual is the fact that it's actually connected to over more nodes and more neighbors that is trying to reduce this tension on those springs also. And so it's doing its best to minimize the error on all the links that it's connected to. So the correct functioning of these protocols is actually very dependent on the fact that the nodes participate honestly with the protocol, and that each node actually blindly accepts information across the network. And this is the impetus behind the attacks in virtual coordinate systems, is that the honest nodes will blindly accept information even if it's from malicious nodes. So we actually classify 3 types of attack, being coordinate inflation, coordinate deflation, and coordinate oscillation, which we'll go over a little bit more detail in the coming slides. And we can show that these attacks not only affect the coordinate system, but any application relying on the coordinate system for estimation of latency or round-trip time. The attacker model we use is a bounded percentage of malicious nodes. The attacker has access to all cryptographic keys stored on a compromised node, and compromised nodes can perform any arbitrary action. So they are Byzantine nodes and can perform whatever they want. In order to evaluate the attacks and the effects of our defense mechanisms, we looked at Vivaldi over the peer-to-peer simulator. We used the king topology, which, as you can see from the graph or the chart at the bottom of the screen, it has 1740 nodes and an average round-trip time of 180 milliseconds. And we use 2 metrics, the prediction error and the relative error. The prediction error is the average prediction error across the system of the difference between the estimated and the real round-trip time on a link. So for King and for Vivaldi, the average prediction error is on the order of a few milliseconds, and the relative error is the error of the system under attack versus not under attack. So the first 2 types of attacks we look at are the inflation and deflation attacks. The first type of attack, the inflation attack, the attacker is actually able to manipulate the metrics to push a node away from its current position. So we can see from the graph, the node under a no attack scenario will be located at the blue triangle, and it has a prediction error of about 10 milliseconds. So if it's about 100 milliseconds away from one of its neighbors, it might say it's 95 to 90 milliseconds, but that's usually an acceptable amount of error for most systems. However, under the attack, it is now pushed to where the red square is located, and now has a prediction error of nearly 70 milliseconds, or 7 times worse than it did under the no attack scenarios. Similarly, the deflation attack actually manipulates metrics to hold a node at its current position. Here we can see that the benign node is once again forced to be held at the origin of the coordinate system and has a prediction error of nearly 60 milliseconds, or 6 times worse than it did under the no attack scenario. So taking a closer look at how these attacks actually occur and what's the actual underlying behind them, we can see that on the left-hand side, there's no attack occurring, and there's little tension on the spring. Now, in order for the attacker to actually perform the inflation attack, he wants to pull the node or push the node towards a desired location. So in the middle graph, we can see that the malicious node, denoted by the red node, is actually able to report a position very far away from the benign node, and a low error which actually caused the node to move towards the malicious node. And similarly, for the third type, we actually have the malicious node. It reports a coordinate close to the benign node, but a very high latency, which actually pushes the node towards a desired location. And so each of these attacks can actually target one or more nodes or subset or the entire actual coordinate system. For the deflation attack, the attacker is actually able to match the real and the estimated round-trip times. So the attacker knows the coordinates of itself and its neighbor node and makes these actually match the estimated latency. And so this will actually causes the node to stay at its current position and will force it to be unable to actually